What we want to do this evening is to absolutely hammer home and fly the flag for what's happening in Wales, because I don't think that, many people really understand the significance of what's going on there. In January, the Welsh Government announced a long-term strategic commitment to support this cluster. It is the world's first compound semiconductor cluster, and more broadly to support all of the exciting work which is happening across technology in the region. So there's certainly a lot to celebrate. Well, luckily I've got a very erudite panel here. And what we're going to do is just to take a look at what this cluster in Wales anticipates it's going to be able to do and what it has already achieved. The thing that's really impressed me about Wales is the amount of collaboration which is happening. Collaboration can make extraordinary things possible, and I've seen some really, really fascinating examples and very real evidence of that. So, first to the stage, could I ask Wyn to step up and talk us through what the CS cluster is all about?
So, in the beginning, I think it's easier to say what we're not. So at the basic level, we're not silicon. And when you think of semiconductors, you tend to think of silicon chips and silicon semiconductors enabling the microelectronics revolution. But we're beyond silicon. So we're a range of materials like gallium arsenide and indium phosphide, and that's where we get our name from, compound semiconductors. We're also not graphene. We're not the material of today or tomorrow. We've been around for about 30 years, slowly getting the world's population addicted to our materials. Started with the internet and the lasers and the detectors that operate under the fiber optic network. Then the lasers inside DVDs, CDs, Blu-ray. Every LED is a compound semiconductor. The most efficient solar cell in the world is a compound semiconductor. And now there's a proliferation of new applications where compound semiconductors are reaching a point of inflection in terms of the number of applications. So what is CS Connected? Really, in recent history, it's a collection of like-minded individuals in the region of South Wales who got together around about 2015 to say, we've got something special here. We've got the seeds of a uniqueness around our academic activities and excellence, our industrial activity, and also alignment with our civic governance and regional government activities. And so that vision, initially back in 2015, I remember writing on the back of a beer mat. It'll take around about 10 million for us to be able to bring this together and really up our game on research activities and the exploitation of our research activities. And 5 years later, we're sitting on a pipeline of in excess of 800 million of investment with a commitment of over 600 million to activities we've already got in play. And so now to say $1 billion, people don't blink in the cluster and say, well, maybe that should be our target. So the ecosystem we've developed stretches around about 60 miles from Microsemi Corporation in Caldicot, near the border, down into West Wales at Swansea University. So we have 10 formal partners as founding members of CS Connected, 4 companies which are involved in the supply chain of materials, device manufacturing, device packaging, and capital equipment associated with that manufacturing. We've got 2 university initiatives at Cardiff University and at Swansea University. We've got the CSA Catapult, which is an innovation initiative funded by UK government. And we've got the CS Centre, my organisation, which is a joint venture between IQE PLC, one of the core industry partners, and Cardiff University. And our ecosystem really is starting to consolidate around a vision. At the moment, we contribute about 180 million of gross value add to the South Wales region, combined turnover about £500 million, with heading towards about 1,600 staff. But the uniqueness about this cluster is that actually we are a connected supply chain. We're just not drawing dots on the map with tenuous links. And the vision is moving towards how do we bring together that supply chain to offer a real advantage and turn this semiconductor advantage into a new era of high-tech manufacturing for South Wales region. So if we look at the supply chain within the region, we have IQE PLC, which is one of the global leaders, very early player in compound semiconductor materials. We have Newport Wafer Fab, which effectively is, at the moment, a silicon process in-house, one of the last large-scale silicon manufacturing plants in the UK, which is moving towards manufacturing compound semiconductors and compound semiconductors on silicon platforms. We have Microsemi, which has a 30-year pedigree in Southeast Wales in terms of development of packaging solutions for harsh environment, for radio frequency and power electronic solutions. And we've got SPTS, which is part of a recently acquired by KLA Tenko, a US company, which is one of the major providers of capital equipment into the fabrication supply chain for advanced semiconductors. So when we take that manufacturing core and put it together with some of the assets that we've got in the academic space within the region and some of the initiatives we've put together, we have something that spans what we call the full technology readiness level space. So we have what we would like to call a seamless path from fundamental research into prototyping and scale up into large-scale manufacturing. We truly believe this is the only place in the UK, and we can probably say the only place in Europe and probably the world where we have this capability that is a vision dedicated to compound semiconductors. And so that's where we want to be on the map. We want to be the first place to say there are 4 semiconductor clusters in Europe, all based around silicon semiconductors. We want to be the first cluster which is known for compound semiconductors. So I'm going to hand over now to Chris, who's going to talk a little bit more about how these supply chains interact and the fundamentals of compound semis. Thank you.
Just to go back to some basics, silicon has been around since the 1960s, actually goes back even further than that. The first semiconductor transistor was developed in 1947, but hardly got any attention at all. I think it was somewhere like page 12 of the New York Times. It wasn't seen as very significant. But clearly, the development in Silicon Valley, lots of companies coming together, it wasn't organized. It was a number of companies that decided, first of all, they probably liked the sunshine, but also there were educational establishments around. Stanford University, for example, University of California, Santa Barbara. And there were also mindsets in capital venture activities and so on. So this attracted a lot of companies. But I guess even today, even though a lot of the Silicon Valley enterprises are basically software companies, if you looked at Silicon Valley and looked at any individual companies, they don't actually talk to each other. It's just a random collection. And I sometimes make the analogy with, if you know Hay on Wye, it's the place to go for bookshops. And you think, why would you set up a bookshop there? There's a lot of competition. Well, actually, you set up a bookshop because everyone knows it as the bookshop city or town. So in some ways, we're very similar to that, except there's a becoming an organization behind linking the dots, as Wynne said. So the process itself is lots of discrete activities, starting with atomic engineering, which is the epitaxy process, whereby we deposit layer by layer at the atomic level, materials including 3, 5, 2, 6 materials, groups 3, 5 from the periodic table, to create these atomic structures that have performance and optical properties that way exceed those that you can possibly achieve with silicon. It's a very intricate process. There's actually only a few players in the world that actually carry out this, and really most of the competition is in either Taiwan or growing in China. The markets we've already touched on, and actually looking at Maggie's list at the beginning of all the predictions from 10 years ago, I would guarantee that pretty much all of them are only possible because of compound semiconductors. So it's had a pretty significant effect on how we live, how we work, how we spend our leisure time, but actually it's invisible. We're embedded right in the center of a lot of these products. And so most people don't even know we're there. If only we could come up with a catchy phrase like IQE inside. Maybe not. But I think it's about getting the word out there that actually compound semiconductors are important to all of these markets. And actually within the UK and even within the region around the cluster in South Wales, we have representatives of all of these industries. They're all using compound semiconductors. Most of them don't even know it. And in fact, we have a history, as I say, of shipping products around the world, and then they're sent back for further processing. But if we talk to the automotive industry, the aerospace industry, on our doorstep. We can actually see one of them. Airbus is just down the road from the IQE site. If we talk to them about the compound semiconductor world, well, they buy laser modules from China. What they don't know is we're probably supplying China with those laser modules. So these things are going around the world a few times without the knowledge of us at one end of the supply chain and the end user at the other end. So it really is quite a fragmented supply chain. What's quite interesting, though, is if you look at the value that's added, semiconductors, silicon and compound semiconductors, are right at the center of the supply chain. Typically, there are at least 8 to 10 processing stages in that supply chain before it gets to the final OEM. So that's why there's such a distance there. And effectively, there's an order of magnitude increase in value as you go through that supply chain. So although we're doing very well in Wales, we have this supply chain from the wafer level through to processed chips. Actually, when you get to the systems engineering end, it's much higher value than just the wafer product. So what we're really looking at is how can we increase some of that processing that's carried out in the UK. And there are typical examples. I've mentioned about our products going around the world and then coming back for processing. But essentially, if we look at the products that leave just a company like IQE, it may be that something like $10 to $15 million worth of wafer product actually ends up as translating into billions of dollars worth in products that Britain is actually buying back in from China. So we're not going to grab all of these supply chains, and we're not going to reshore everything that we do. And actually, for a lot of the historical products, there's no chance of getting those products back. But actually, we're on the verge of new and emerging technologies, autonomous vehicles, a lot of healthcare sensing technologies and so on. And UK actually leads many of those technology leaps. So we don't see any reason why we, and particularly around the cluster in Wales, we cannot grab more of those manufacturing processes. So our aim is really to grow the supply chains and to actually encourage foreign direct investment, startups to actually locate somewhere that they can access easily the work of the cluster to turn those products into made in the UK type products. And we believe we have a very good chance of that, given the fact that we have both the supply chain from TRL1 all the way through to TRL9, so from research through to volume production. All we need to do is to make sure that we can fill in some of the gaps in the supply chain. So we're confident that we have the centre of something that really could be quite exciting. And on from there, I'll pass over to Andy.
So I represent the Catapult, the Compound Semiconductor Applications Catapult. We're the 9th Catapult in the UK. The Catapults are a programme. There are research and technology organisations doing translational research. In total, it represents about £1 billion worth of investment by UK government. The Compound Semiconductor Applications Catapult works very, very closely with IQE, with the Compound Semiconductor Centre and other members of the cluster, and we're the only catapult to be solely based in South Wales. So what we have done is we've actually surveyed the market. This market is an enormous market. It's currently valued at about $77 billion, projected to grow to about $300 billion by 2030, growing with a CAGR of about 12 to 15% annual growth rate. It's a phenomenal market. Now, compound semiconductors do things that silicon chips don't do. So fundamentally, we will not displace the silicon chip as a computational device, but compound semiconductors do three things that silicon chips can't do. They do power, speed, and light. So they do power conversion, which is power electronics, electric vehicles. They do speed, which is RF communications and microwave communications. And they do light. So they do the detection and the emission of light, otherwise known as photonics and sensing. So we've color-coded those three different areas of applications, blue, green, and red. And we've surveyed the market to say, how big is this market? How fast is that market growing? And how much of that market can the UK tap into? Because fundamentally, we're about working with our partners to boost economic activity for the UK. And so this graph actually represents, on the y-axis, it represents the market opportunity. How big is that market? How fast is it growing? And on the x-axis, it represents the UK capacity to exploit that market. How many companies do we have? How many SMEs? How many large companies? How many academics do we have working in this space? And you'll see we've got like a primary focus zone and a secondary focus zone. So you'll see that the digital economy, a blue market opportunity, a global market opportunity of about $10.5 billion, and a UK market opportunity of about $510 million. This is our number one priority. So that is things like digital economy, is things like data centres. So in the audience, we actually have a representative from Next Generation Data Centre. That's Europe's largest data centre located in South Wales. Data centres are now are attributed to a large proportion of the energy consumption use. And these guys are putting in racks that consume hundreds of kilowatts of power. You need compound semiconductors to regulate that power. They're much, much more efficient. Actually, just out of the secondary zone, we've also even looked at quantum technologies. So quantum technologies, it's a new and emerging technology. The UK is investing around £300 million at the research base in this space. It's projected to be a global opportunity of $5.3 billion. So compound semiconductors are fundamental to quantum technologies. They're fundamental to the generation of single photons and to the detection of those single photons. And where quantum technologies could lead, quantum cryptography for financial transactions, sensing, gravitational sensing, looking at underground pipes and buried structures and what have you. So the UK already has a lot of research going on at the research base, and this is another area of interest for us. And another area on the RF is the defence. So defence about radar and beam steering and high-speed data communications, another area where the compound semiconductors are preeminent. So in terms of sort of building and completing the supply chain, so Wyn and Chris have mentioned that within Wales we have this unique cluster of activity spanning from the research base right the way out to final products. And the catapult is just one part of that linkage in the supply chain. And the catapult, looking at applications, kind of represents the end of that supply chain. So Chris talked about the supply chain going from a wafer to a die to a chip, and into a system and then ultimately out to a product. And one method that the catapult is helping to accelerate these applications is through the development of evaluation modules, whereby we can actually put devices on there and allow companies to evaluate those devices and take those devices faster to market. I've got sort of 3 examples of projects that we're working on at the moment. The catapult is already working on a £20 million project to develop the entire supply chain for the electric traction of McLaren sports cars. So this is a silicon carbide fabricated in the UK to produce a power electronics module that will go into a McLaren electric sports car. McLaren are a highly innovative company, a sort of an early adopter. Once we've got this product into market, we can then look at sort of higher volume companies later on. So we can take this same technology into Jaguar Land Rover, BMW, Mini, etc. So this is about early adoption and getting those products to market. The catapult has a £5 million product, a £5 million project to develop a gallium nitride process. This is taking a process from Cardiff University, which we're then commercialising and upscaling. That will give us a sovereign capability to make high-speed data communication chips for RF communications, things like 5G networks, things like radar, and so on. Again, it's a sovereign capability that the UK will have. And we've actually just completed a project, a distributed Internet of Things project, whereby we're using distributed fibres to monitor rail infrastructure. So again, it's another project that the catapult has just completed. So we are working very, very quickly at getting these projects to market. So where do we think these sort of 1 trillion devices are going to come from, and how will the compound semiconductor cluster sort of be able to address this? Well, there's a whole range of applications which are just starting to emerge. So I've mentioned the data centres. Data centres about high speed getting data in and out of the data centres, portable mobile devices, and the power control within those data centres are all going to require compound semiconductors. Next generation communications, so the 5G infrastructure, and then Again, it's reliance on satellite communications, and Maggie alluded to the fact that there are 4,900 satellites. Those satellites require compound semiconductors. Silicon does not behave very well when you subject it to radiation in outer space. You need compound semiconductors to generate the power, to do the satellite communications and the downstream data communications. Smart cities, how we communicate with smart cities. And I mentioned our IoT project where we've got embedded fibre sensors looking at rail infrastructure. There'll be more and more of these sensors, and this is how we're going to get to 1 trillion connected sensors. Autonomous vehicles. Maggie mentioned the autonomous vehicles and how 40% of vehicles will have connectivity by 2025. All of those vehicles are going to require compound semiconductors. This is a massive growth opportunity. Robotics and automation. Robotics require sensors to sense their environment, the things that they're handling, and they require high-speed data communication to relay that data back. Sensing, different sensing applications. Smartphones at the moment, the latest generation of smartphone uses facial recognition. That has an array of infrared lasers on the front of the smartphone. When you open the smartphone, those lasers scan your face and are able to build up a 3D image of your face. Those 3D lasers, that laser scanning technology relies on compound semiconductors. So the future is really incredibly bright for this technology, and we have an incredible cluster of activity that we're building in South Wales that will be able to address this.
Thank you very much indeed.